Welcome to the discussion on the topic elastic constants and relations. This is one of the topic under the unit stresses and strains in the course strength of materials 1. I am hoping by the end of this particular short discussion you will be able to at least understand the following things. The elastic connects, you'll able to relate to that, and we're able to see and rephrase the relations between Young's modulus and bulk modulus, as well as all the three: Young's modulus, shear modulus, and bulk modulus. In the previous session, we have already learned the relation between Young's modulus and shear modulus. Now, before going to their relationships, let us just review for a short time about the what is these Young's modulus, and what are the basic definitions of these various moduluses. So we have discussed in the previous session also there are four essential elastic constants that deals all kinds of loading, whether it is normal load, normal kind of loading, or shear loading, or even hydrostatic loading. Whatever may be the type of loading, we generally deal with these four elastic constants, namely Young's modulus, shear modulus, bulk modulus, and Poisson's ratio. By definition, Young's modulus of elasticity is nothing but direct stress by direct strain, which can also be direct stress can also be referred as longitudinal or normal stresses, and the corresponding stress and strain, if you consider that longitudinal stress and longitudinal strain, you will be able to get Young's modulus. Or same thing, no, the names are also applicable here, normal or direct stresses. When shear stresses are acting on a system, the corresponding modulus you are going to get is the shear modulus. Another name for that is modulus of rigidity. Then comes your Poisson's ratio, which is nothing but the ratio of the lateral strain to the longitudinal strain. In one direction, suppose you are applying a kind of stress in one direction, that direction becomes longitudinal direction. The other direction, suppose it is a two-dimensional only, you are applying x direction, the force that becomes your longitudinal direction, the y becomes your lateral direction. So if it is a three-dimensional, if you are applying in x, y and z becomes your lateral directions, and the corresponding or associated strain in those directions can be referred as lateral strain. Coming to the bulk modulus of elasticity, it is the ratio of stress that can cause change in the volume to the volumetric strain, right? So knowing these basics, we can straight away go to the relationship between Young's modulus of elasticity and bulk modulus of elasticity. Let us consider a small cube where cube means all dimensions are same, x, y, and z, and in this particular uh, uh, derivation that we are going to do, we are taking a kind of force system acting on a particular particle where all the stresses are almost same. Such a situation may arise somewhere the force is acting on a under a in a fluid system, or on a force is acting or stress is acting on a soil particle, right? So where all the stresses are equally placed in all the three dimensions. So we can calculate first of all what is the strain in any one of the direction. If you try to calculate the strain in x direction, for us supposed to say epsilon x, let's say here we are calculating the total strain in one of the direction, like one edge, if you want to calculate, because of the kind of hydrostatic stress as I just mentioned. So if you try to calculate the strain in one of the direction, let's say x, this is x and y and z, you can calculate in x direction. Doesn't matter because all three are same. You are going to get whether it is sigma x or sigma y, sorry, epsilon x or epsilon y or epsilon z, it will be the same. So sigma by E, that is the, because no, we are because of this stress we are calculating because of this stress, so that becomes your direct strain, that is the longitudinal strain, that is straight away sigma by E. And because of the other two stresses here, the sigma acting in y and z direction, these two stresses become no, they, what they will do for this direction, these two stresses, because of this stress there will be lateral strain in this direction. Similarly, because of this particular stress there will be lateral strain here. So altogether you will have three strains. One is longitude, other because of this one there is a lateral strain here, because of this one there is a lateral strain here. So because it's a tensile force system, the first one is sigma by E, straight away you will be getting stress by strain is the stress by Young's modulus will give you the strain in this particular direction x because of sigma. Because of this sigma, you will be getting Poisson's ratio times your stress by strain. So sigma by E, and similarly due to this sigma, the stress acting in the z direction will be getting minus mu times sigma by U. So finally, you will be getting, upon simplification, if you take common sigma by E, you will be getting 1 sigma by E times 1 minus 2 mu, where mu is the Poisson's ratio. Then, if you want to calculate volumetric strain, we discussed in the previous section, on the topic of volumetric strain. It is nothing but the strain in x direction, summation of x strain in x direction, y direction, z direction. Of course, here all three are same stresses. Therefore, the resulting strains are also same. That is epsilon x, epsilon y, so they all there become equal. So when you want to calculate volumetric strain, in this particular case, this becomes 3 times sigma epsilon x. That can be epsilon x or epsilon y, epsilon any linear strain, right? 3 times the linear strain. So linear strain already in x direction we have calculated it. That is 3 sigma by E times. So 3 into sigma by E times 1 minus 2. The totally it becomes 3 sigma by E times 1 minus 2. Once you have calculated this, you can now use the definition of the bulk modulus. We have just got the volumetric strain. As per the definition of modulus, bulk modulus of elasticity or bulk modulus, we have just now discussed right in the beginning. That is the stress by volumetric strain. So based on that, if you want to calculate from here again, we already calculated volumetric strain and kept there in the previous step. So now you from here also you can calculate your volumetric strain. Bring this volumetric strain to the left side, then K comes to the denominator and the volumetric strain becomes now sigma by K. And then your sigma by K here, this here sigma by K is equal to 3 sigma by E times 1 minus 2 mu. By equating the strains, you will be getting so we have calculated the volumetric strain here and kept it. Now the volumetric strain as calculated from the definition itself. Straight away we have rearranged the terms, that's it. So volumetric strain is equal to sigma by K. How we got from the, no, I just now told. So from the volumetric strain and the value which we have calculated just before, from here, right, 3 sigma by E times 1 minus 2 mu. Now we can equate that to this volumetric strain. Therefore, will be finally will be getting this kind of formations, right? So if you equate both the terms, you can straight away get the value of Young's modulus in terms of bulk. So this is the relationship. E is equal to 3k times 1 minus 2mu, where is Young's modulus, k is the bulk modulus, and mu is the Poisson's ratio. Now, at this juncture, if one wants to write, bring in the shear modulus also into picture, what we can do is we can eliminate one of the constant. So which constant we can, suppose I want to get a relation between Ek mu, this is the equation, but if I want to get an Ek and G, which is called shear modulus, so in that case we can use uh, we can take the mu out, and there we can keep the uh, G value into picture. How to do that? So we can simply remove here. We have the relationship E equal to 2G equal to 1 plus mu and E equal to 3K into 1 minus 2. You can simply rearrange the terms. Let's say this mu. If you move this to other side, you can find out the value of u and take them out. So E by 2G minus 1, you can write. E by 2G minus 1, and that must be equal to, right, from here also we can get the value of mu, right, how 1 minus, right, E by 3K, if you rearrange the terms, by 2 is what here, right? We bring this E, this 3K this side, E by 3K, and bring again to this side. So 2u comes this side, so 1 minus E by 3K, right, divided by 2. So if you simplify this, you will be getting, you can separate the constants one side. You will be getting the relationship, this relationship, 9gk by g plus 3k. Right? So that's how you get the relation between E, G and K. Now once you got the, because there are no other terms here, you can see except E, K, G, nothing is there. So mu was just taken outside. So you can get the relationship. Then if you want to get the relation between E, K and mu, right, which we have already done. From that relationship, if one wants to get only in terms of other three constants, namely Poisson's ratio, Young's modulus, and shear modulus. Sorry, bulk modulus and shear modulus. Okay, we want to eliminate E, in other words. So E can be eliminated by equating these two. E can be eliminated, and we can get an equation in terms of kg and mu. So this is the relationship. So in that way, finally we came to know the relationship between all the elastic constants, right? Namely, in the previous section we have seen E and G, right? Now we have seen in the previous section E and G. Right? Now we have seen the relationship between E and K, EK mu, right? Also between EKG, Young's modulus, bulk modulus, and shear modulus, as well as Kg and mu. So all the three relationships you have seen. So that's the intention that with which we have started this discussion. Right? I hope you got it. Thank you very much.